Okay, this brings us to the moments we've all been waiting for, the end of the course. As we wind down, we've been talking about a lot of doom and gloom that has occurred, that has faced humans over the last couple 100,000 years. We have a future, maybe, ahead of us. And what we'll talk about today for a few minutes is whether that's going to be a good future, a promising future, or a troubling future. And just as a heads up, I'm going to say it's all about the batteries. So we'll use a house as an example of changes that we can make right now. Now we can talk about sports cars and motorcycles and all kinds of electric vehicles. But one thing that we all have in common is not that we drive sports cars or motorcycles, but we live somewhere. So that's where we can make probably the biggest immediate dent in cutting our dependence on fossil fuel. So let's start out with a house, an energy efficient house. Now, you might imagine that an energy efficient house, a greenhouse, might look something like this or something like this. These are both possible, but not particularly attractive and not particularly as efficient as they could be. The first thing to consider if you're building a house and how you're going to make it a clean or green energy house is going to be where are you going to build that house. That's going to be driving your decisions. At least it should drive those decisions. If you're building a home in Costa Rica versus a home in the Yukon, obviously weather jumps out at you immediately. The climate of the two locations differs considerably, and therefore your energy needs are going to differ considerably. The big energy items that we're going to be concerned with today are going to be the heating of the house and the heating of water used by the household. Electrical appliances is going to be important, and ultimately lighting, electrical of the house itself, how the house operates, and the windows are going to be important. Are there others? We can take a look here. This is a basic layout of how energy is used by houses in the United States. So I would anticipate it's going to be fairly similar for Canada. I haven't found this type of breakdown for Canada yet. I'm sure it's out there. What do people use energy for? Well, heating and cooling is about 50% of the energy use in your home. In the Yukon, this is going to be heat. In Costa Rica, it's going to be air conditioning. Maybe, if you have that option. Domestic water heating, this is water for, hot water for a dishwasher or just washing dishes. Hot water for a shower, or washing your face, hosing off your dog, things like that. That accounts for about 1/6 of your energy usage in any given year. So right there, we have a considerable amount of energy used just for making things hot or cold. And about 61% goes to basic heating of air and water. Okay, so that's a big one. That's the one we're going to tackle first. Now, we have additional heating needs that are odd in some other ways and a little bit more difficult to deal with, such as, say, an electric oven. We can supplement that with other sources like a wood stove, for instance. Refrigerator, got to keep things at a regular temperature, so it's hard to get around that. Washer and dryer. The dryer is going to take up a considerable amount of electricity, heating up air to make your clothes dry. The washing machine is going to take up a considerable amount of energy in generating hot water. So again, we're back to a heat issue. The vast majority of our needs are for heating and cooling. So we can make some basic changes easily. We can use energy efficient bulbs. We can use energy efficient appliances. We can unplug things that require a vampire load, and there's a list here. If you've never heard of a vampire load, this can be considerable. In fact, about 35% of the energy that's used in any given year is wasted. So this is another way to cut back on your use of power without influencing your life in any negative way. Just turning things off that you don't think are using electricity, but are. The insidiousness of the vampire lifestyle. So you want to build an energy efficient house. The first step is insulate it. The second step, insulate it some more. And the third step, make sure the house is well insulated. There's nothing you can do. There's no way you can save more money. There's no way you can save more energy than to insulate the place you live in to the degree that you can. So here are some examples of some insulation you may not be familiar with. This is called geofoam. This is laid down on the ground underneath a structure. So this provides however much insulation you want. You can make these into thin blocks or very, very thick blocks. And these insulate the building from the ground, just like insulation in your attic influences your ceiling from the outside air. We can also put foam insulation into cinder blocks that are used for wall construction, thereby increasing the insulation value of those walls, cinder block walls, which are fairly cheap. And inside a house, whether it's an old house or a new house, we can insert multiple layers of different kinds of insulation to increase the what's called the R value of a home. That's the insulation value. Now, windows obviously are important. We use them to let light in and to see what's going on outside. What's that horrible sound out? Is that an animal trying to get into my garage? Things like that. You need to look outside. A couple ways to do it. We'll start out with a fairly simple modern way. This is using what's called low E glass. This is glass that is coated by, they have a couple different ways to do this, but one is just coating the glass with a surface that allows radiation through, long wave radiation through in one direction, but it's not allowed to escape in the other. So in the wintertime, if we use a super system that includes a double pane, so sort of a doubling up of this to this, we fill the space with argon or krypton, two noble gases that aren't going to react with anything. So they provide a clean space that's not going to be subject to condensation or corrosion or any other problem you have if you just put air in here. So again, we have a low E coating that allows light through. In the wintertime, the infrared radiation does not go back out, so the heat that's in the house stays in the house. The light in the summertime tends to bounce off of the glass, so we don't heat up the house in the summertime. These kinds of coatings keep the place, your place, cooler in the summer and warmer in the winter. I have something like this in my house I installed about 10 years ago, and you could touch the glass inside the house and it's warm. It is just as warm as any other surface in the house. Therefore, it's not communicating with the winter air outside in any direct way. So it's very, very efficient. Also pretty expensive. One of your biggest costs is going to be windows. Now, we've got a house sealed up, insulated, good windows, we're sealed in, but it's cold, so we need to make it warm. Currently, most houses are heated by coal that supplies electricity for baseboard heating, oil, which can be used to heat a boiler that could be pumped through in a radiator system, or natural gas most commonly. More than 50% of houses in Canada use natural gas. It's in a furnace, and you have ductwork that blows hot air throughout your house. Now, if you've got enough trees on your property to supply wood in perpetuity, you cut down a few trees every year, but by the time you worked your way across the property, those trees have been replaced by fully grown trees, so you're self-sustained in terms of wood. Now, wood-burning stoves have come a long way in the last 10 years or so. They're much more efficient now. They take air from the outside, so you have a conduit connected to the outside. So you suck air from the outside into the combustion chamber. It's heated, generates radiant heat from all surfaces here, including the chimney, and then the hot gases exit the house. So there's no pulling in of cold air. This is why fireplaces aren't a really good idea for heating a home, because all the heat that's generated going up the chimney is replaced by cold air. That hot air has to be replaced by cold air. Therefore, you're warmed by the fireplace, but anywhere else in the house, air is streaming in as much as possible. So we have an external air supply. We have an auto damper control. This means you can set a timer essentially for these things. You stuff it full of wood and you tell it you want it to burn for 14 hours, so you go to sleep. You wake up in the morning, it's still warm in the morning because the stove is still burning. You can throw some more wood in there and your day is off and running. There's a thermal inertia possibility for these stoves now. You can coat the stoves in serpentinite, soapstone. You can wrap them in a water jacket. Both of these will absorb heat and then give it off slowly. And you can employ a series of baffles to direct the gases around in here, and catalysts that also fully combust the gases in here rather than let good reactionable material fly up your chimney and out into the world. Big improvements in the wood stove business. Wood boilers have come a long way as well. These are used to heat water that then flows into your house, into your hot water system, and it becomes your domestic hot water in the house. You can up that a couple notches by incorporating it into radiant floor heating that we'll talk about in a few minutes. And therefore you could use a boiler to heat the house, the air in the house, and supply all of the hot water needs for personal use. We can start out with solar wood boiler radiant heating, and we need to get that into the house. We don't want it flowing through ducts. We don't want to blow hot air around because that's not a good idea for a number of reasons, including noise, dust that blows around, and it's hot, dry air that turns you into a potato chip over the winter, dried up and moisture free. So some companies design these floors that you can just literally roll plastic tubing in called PEX. This is good for about 200 years, longer than most of us will live. These tubes are continuous, so there's no chance for leaking unless you pound a nail through it or do something crazy. So a long plastic tube runs through each floor of the house or each room of the house, sourced from a device like this. Now, once water is warm and in here, it's free to flow about the house. You can control it by your phone, change the temperature of any given room. It's really neat. The radiant floor heating is nice because the heat is created in the floor. The floor itself warms up, and it's a huge radiating surface. The warm air rises from that floor. If you go to the second floor, it's going to rise from that floor as well, or down in the basement, rise from that floor. It's a slow, steady supply of comfortable heat. There's some other ways to do this. In addition to a wood boiler, we can install a roof system of solar tubes. In this case, these tubes are filled with water or antifreeze, some kind of ethylene glycol mix. This works great if the temperature doesn't get too low. So in Costa Rica, this would be a great way to generate hot water for showers. It won't work here because this would freeze. If you use antifreeze in it to keep it from freezing, you're still going to have water flowing through these tubes that is minus 40, or ethylene glycol flowing through these tubes at minus 30, minus 40, whatever the outside air temperature is. So that's no good. Doesn't help us here. It helps you up to about the northern boundary of the US and Canada, essentially, is where these no longer are of significant use. So we're going to turn to something fancier that's actually been around for a while. And these are cheap, these are expensive, but these work anywhere. They work where it's very cold, and they can work where it's very hot. So these are solar vacuum tubes that absorb incoming radiation. These are essentially perfect black bodies as long tubes inside these larger glass tubes. So radiation strikes those black bodies, is converted into infrared radiation, and that heats up the tube, which heats up a fluid, which then flows into one of these tanks. And you can see inside these tanks are a series of coils that serve as a heat transfer. Now, one reservoir here is used for internal hot water for your shower, tub, dishwasher, general hot water usage, and the other is routed through the radiant floor heating system of the house. If there's a particularly cold period, this can be supplemented or boosted by inserting an electrical conductor into this and powering that from electricity. Now, how we get our electricity, we'll talk about in a minute or two here. So there's the solar power to heat the water in the first place. If we use too much of this hot water for heating the house or domestic hot water, we can boost that heat via an electrical conductor that's placed inside this device. So we've got a backup. Now, if the solar backup isn't sufficient, we can use an electric generator as well. So why are these better than the flat panel collectors? Flat panel collectors are cheap. If you've ever been outside in the summertime and had a drink of water from a hose, you know that you let it run for a while because the water is warm or hot. In fact, if the hose is lying in the sun during the afternoon, it can be very hot, uncomfortably hot. So that's cheap. It's as cheap as a hose in the sun, which is great as long as it's warm. If it gets cold, that no longer does the trick because the cold air is going to suck the heat out of those tubes and return it to the atmosphere. Now, for solar orientation, one of the cool advantages of these is their tubes. So they're round. If the sun is over here, it's going to strike the tubes perpendicular to the direction of the sun. If the sun is up here, same thing. If the sun is over here, same thing. Over here, same thing. No matter where the sun is, it's going to strike these tubes with essentially the same intensity, the same perpendicular angularity relative to the source of radiation. The complexity of this system is pretty minimal. It is a tube inside of a tube that's been evacuated. Let's say you have some crazy kids or wild animals running around and they break one of these tubes. You're out $715. Or, in this case, these tubes pop out. So you can just pop one of these out of the array, pop a new one in for about, I forget the price, like $30 or so. So for $30, you can fix a damaged tube, or I assume just seal it off and not use that space. So for most hot water systems, for most homes, one of these arrays would work. For another $715, you can double your water heating capacity. And for another $715, you can triple it. So most people use these initially just for hot water in their house, just for showers and so on. If you want to use it to heat the house, then my calculations are you would need 2 or 3 of these to heat a 2,500 square foot home and the hot water needs. So now we've got the heat we need to stay alive and the heat we need to heat water to make staying alive worthwhile. But we like electricity. We want some power. We want to record lectures on our laptops in small abandoned rooms in our houses, like I'm doing now. So you've all seen solar panels like this on houses. These are pretty common. Advantages, they're out of the way. They're on your roof. Disadvantages, they're on the roof. And if they get covered with snow or something else, somebody somehow has to clean them off. A solution to that is put them on the ground where you can reach them. You may install motors that track the sun. Those are pretty expensive. And for personal use, it's not worth it. I've done, again, some calculations on that. It's just not worth it. You can put some reflectors, though, near here that'll boost the incoming radiation and surface by 30%. So a couple pieces of cheap sheet metal, if you're not looking for an attractive solution, would boost your solar panel output by 20 to 30%. Tesla has taken it in a bit of a different direction. They've designed solar roofs. These are solar panels. They look just like terracotta, asphalt, or slate shingles. And they're almost as efficient as these. So you can have a completely normal looking house that is one big solar collector. Solar panels themselves and the batteries is 20 years. So you should get 90% of the power in 20 years that you get out of these today. So during the day, these generate all the power you could need. If you need more power, add more panels. If you need more power at night, well, you need to store the energy somehow. With vacuum tubes, you can store heat in water tanks and extract that hot water in the middle of the night if you want. For electricity, we need batteries. So this is a thermal battery, water. Electricity is going to need electric batteries. Generally speaking, most houses, again, around 22 to 2,500 square feet, 3 or 4 people, you use about 10 to 12 kilowatt hours per day. So these are some guesses. This is a Tesla Powerwall 3 that's not out yet. It's anticipated it'll be around 26 kilowatt hours. It's anticipated it'll cost around $12,000. I'm guessing it might be a little bit more than that. This is US. Probably around $14,000 to $15,000 plus $5,000 for installation. So we're looking at around $20,000 for Powerwall 3 when it comes out. But this will cover you for 2 days, 2 power-free days if something goes down with the grid or if you're not on the grid. A German company, Sonnen, makes solar batteries as well, very high-quality solar batteries that are about 30% more expensive than the Tesla batteries. They have software that does a bit more than the Tesla Powerwalls do now, but they're still more expensive. And again, like the solar vacuum tubes, if you want more power, you can buy more of these. You can string as many as 10 of these together. And that would easily be enough to power a business. And the same goes with the Sonnen. You can string a whole bunch of these things together.
Looking for fun and feeling groovy.